we've learned that if you take a uniform magnetic field, and let me draw that, we know this field is uniform because the field lines are parallel and evenly spaced. And if you send a positive charge or a negative charge through, I'll send it over to the right, it feels a magnetic force. We stick our thumb in the direction of the velocity, our fingers point with the field lines, and we use our right hand. So if you do this, your palm is facing out of the page. So the force, the magnetic force, points out of the page. There are things that affect how big the force is. For example, if the charge Q is really big, it feels more force. If it's going really fast, V is big, again it feels more force. And if the field strength, if you have a really strong field, again you get more force. The magnetic force is equal to the product of these three things. But there's another quality that matters. What if you take the charge and you send it through like this? Well, you will still get a force out of the page. The direction of the force hasn't changed, because if you take your thumb and stick it with the velocity, stick your fingers with the field lines, and you use your right hand, your palm is still facing out of the page. So the direction hasn't changed. But what about the magnitude of that force vector? It does change. Consider this angle theta, which is the angle between the field and the velocity. You get a bigger force when theta is 90. Bigger force. And you get a reduced force if it's going at an angle. That's smaller. And if you take your charge and you send it through so that it's at 0 degrees, it's angled 0 degrees away from the field line, in this case that I just drew, theta is 0, you get no force. What trigonometric function do we know that yields a big value for 90 and 0 value for 0 degrees? The answer is sine. And this angle theta is the angle between the velocity and the magnetic field. So I like to write subscripts to remind myself it's the angle between velocity and magnetic field, the angle between those two things. And that's an equation we're going to use. But the same way we have a single charge that feels a force, what if we take a magnetic field? Here it is. It's a uniform field. And we take a wire like this. And the wire has current traveling this way. Well, current is kind of like charge. And which way the length passes, that's kind of going to be like velocity. And then we still have the magnetic field B, and there's still some angle between, the length of the wire, and here's the length L of the wire. There's still some angle between that length and the field line B. So the new equation is going to be the length L, let's do it this way, the current I times the length L times the field strength B. And again, we have sine of theta VB. It's pretty easy to derive this. If you take the top equation, well, velocity is just distance over time times B sine theta. And Q divided by delta T, that's current, right? Equals current I. And distance, that's kind of like the distance of the wire, L. And so we can see where that equation might come from. Now, this is not a really rigorous proof. I'm not deriving anything really in this case. because I'm really ignoring some important directional considerations, but it's a way to think about where this equation comes from. It gives us some intuition. We see those equations in our notes on this page, on page, what is this? 20. And so now we're going to start to use those equations. If we turn to page 21, we can try 13 together. A wire of length 45 centimeters. Now we're going to write that in meters. That's L. Carries 1.5 milliamps of current. That's I. Current is I. 1.5 milli is equal to 10 to the minus 3. So I substitute in for the prefix. And it carries this current through a magnetic field of uniform strength 2.8 Tesla. That's B, the strength of the field. The direction of flow and the direction of the magnetic field are shown below. So charges are going up this way. It's like the velocity points upward, if we think about their velocity. Okay, so your thumb points with the velocity. It just says current, so we assume it's positive charge. So we're using our right hand. Our thumb points up. Our fingers of our right hand point with the magnetic field lines. And if you think about this, your palm is facing into the page. So force, magnetic force, is into the page. Okay, calculate the magnitude of the force. Magnitude, that's what we get from the equation B times I times L sine theta. And this is the way it's written in our data booklet. Not the way that I showed you before, but this is the form they give. So the value of B is 2.8 Tesla. The current has a value of 1.5 milli, so 10 to the negative 3 amps. And then the value of the length is 0.45 meters. Okay, I'm out of room, but what's the angle? Well, theta is always the angle between their velocity, and they're traveling upward, right? Because current goes up. It's the angle from the velocity vector to the magnetic field vector, which is 90 degrees. And sine of 90 is just going to be, this is times sine of 90 as well, that's just equal to 1. So in my calculator, I do 2.8, let's make this smaller, 2.8 times, let's see, 0.0015 times 0.45, and I get, wow, quite a small force, 0.0019 if I round for sig figs. The Newton's unit for force is newtons. That is the magnetic force. If we wanted 1, 2, 3, 10 to the minus 3 is milli. This is 1.9 millinewtons. And that's how we solve these problems.